Hi everyone, in this video I'm going to talk to you about section 5.3, which is two new identities that we're going to be using. They are the sum and difference identities for the cosine function, and then in the very next section we'll talk about sum and difference of sine and tangent functions. Okay, so this slide, it might look overwhelming. Don't worry too much about it. This is just the proof for where the identities come from, how you can derive them. Feel free to pause this and take a look at this slide. But I'm not going to test you on this, on how to derive the identities. I'm just going to show you and focus on how to use them. Okay, but this is where they come from. This is the proof of how you get the sum and difference identities for cosine function. Okay, so here are the two identities. Notice what you have on the left. You have cosine of a plus b. So you can think of that as the sum of two angles, and then you're taking cosine of that sum. And then also on the left, cosine of a minus b. So the difference of two angles. That's why it's called cosine of a sum or difference. And so what this allows you to do, these two versions of this identity, is you're able to break apart the sum of two angles and the cosine value of it based on individual cosine and sine values. So you break this apart. Instead of a plus b, you now have individual cosine a, cosine b, individually sine a and sine b. And then very similarly for the difference equation, cosine of a minus b, you can break it apart again with cosine a, cosine b, but this time with a plus sine a, sine b. So notice the only two differences in these two equations is the plus and minus. If you have the sum of two angles, well, the formula on the right side has a minus, a difference. If you have the difference of two angles and you're taking cosine of that value, the formula on the right has a plus. So notice it switches. Plus, minus over here, minus, plus over here. Okay, so you want to have these identities available to use in the next examples. Okay, so we're going to take a look at this first example. Notice it says find the exact value of cosine 15 degrees. So if you think about your unit circle, 15 degrees is not one of the angles that we found the exact value of. And so what you're able to do now, using these formulas we just mentioned, is you're able to rewrite 15 degrees in this case, as either the sum or difference of two angles we do know something about. Okay, so this requires just a little bit of investigation. You're going to take a look at your unit circle and think about how can I get 15 degrees from angles I do know about, angles I do know cosine, sine, and tangent values of. And so if you focus over here your attention in quadrant 1, take a look at these values and think about how you can get a 15. Okay, think about how you could possibly get 15 from any of these values over here. And hopefully you're thinking along these lines. If A is 45 degrees and B is 30 degrees, if we subtract them, we will get 15 degrees. Okay, so that just requires that we think about it, we look at our unit circle, and then we come up with those numbers. And so what that lets us do is rewrite cosine 15 degrees as cosine of the difference of 45 minus 30 degrees. Okay, and these two angles we know about, we know cosine and sine values of these two, and now we're going to use our difference of angles, our difference formula, excuse me, for cosine of two angles. And so let me remind you what that looks like from the previous slide. So cosine of a minus b can be rewritten as the product of cosine a times cosine b, and then you add the product of sine a times sine b. So everywhere there's an a, I'm going to fill in 45 degrees, and everywhere there's a b, we're going to put 30 degrees. Okay. Now, each of these four values, we know these either from your unit circle, or if your calculator gives exact values, using your calculator in degree mode. So each of these four values, we're going to fill this in, and then we have, notice, a product of the first two. The formula says to multiply the first two cosine values, then multiply the second two sine values, and then add the result. And so we end up with, final answer, square root 6 plus square root 2 all over 4. Okay, let's do this again. Now this time we're going to find the exact value of cosine of 5 pi over 12. So we're using radian measures. And on this one, if you think about your unit circle real quick, there's no denominators pi over 12 unless you've rewritten them yourself. So what we're going to end up doing is having to change some denominators around, but it's not that bad. So the goal here for now is to figure out how can we rewrite 5 pi over 12 either as the sum of two angles we know about or the difference of two angles we know about. So taking a look at our unit circle again, like I just mentioned, there's nothing here around the whole unit circle with a denominator of 12. Okay, but it's very easy to rewrite our denominators. So if you focus your attention on quadrant 1, we're going to take our angles in quadrant 1 and rewrite the denominators to be over 12. Okay, so for example, pi over 6, if you just multiply top and bottom by 2, you get 2 pi over 12. And we do that for pi over 4, pi over 3, and pi over 2. And so think about it for a moment right before I show you, and think about how you can possibly get a 5 pi over 12 using these values. Right? So hopefully you're seeing it, and what we end up with is if we add 2 pi over 12 plus 3 pi over 12, we do get 5 pi over 12. But we're going to use the version's simplified denominators, so this is the same as pi over 6 plus pi over 4. Okay, so we can rewrite cosine 5 pi over 12 using cosine pi over 6 plus pi over 4, and we know about these two angles. So we're going to use our sum formula. So back from our two identities here, cosine of the sum of two angles can be broken down as cosine A times cosine B minus sine A times sine B, where A is pi over 6 and B is pi over 4. Okay, and so we know all of these values, these four values, from our unit circle, or you can use your calculator if it gives exact values in radian mode. And so we plug in our values, final answer, square root 6 minus square root 2, all over 4. All right, let's try one that goes the opposite direction. So this example says find the exact value of cosine 87 degrees times cosine 93 degrees minus sine 87 degrees times sine 93 degrees. So if you think about it, this is actually one of our sum or difference formulas, but it's the right side of the equation. So we're actually working back toward the left side of our equal sign. Okay? So what does this equal in terms of our sum and difference formulas that we've just talked about? Well, this looks just like cosine of an angle A times cosine of an angle B minus sine A times sine B. And if you look back at your notes, this is cosine of A plus B. Okay, so this is a sum formula, sum of two angles for cosine. And so if you go back up here, let's fill this in. This is cosine of 87 degrees plus 93 degrees. And then we can just go ahead and add that together. This is going to give you cosine 180. And we know cosine 180, or cosine pi, from our unit circle, is just -1. Okay, so we're going to go to the cofunction identities now. And we've talked about these in the past. We've learned about our cofunction identities. But what I want you to recognize here is that this is already what we've been talking about in this section. These are the difference of two angles. Okay, so that's why it comes up again in this section. Cosine of 90 degrees minus theta. So this is like cosine A minus B equals sine B in this case. And our other 5 cofunction identities. Okay, a quick note, just remember if you're in radian mode, you can just use pi over 2 as a replacement for 90 degrees. Okay, so let's try this example here. Find one value of theta or x that satisfies each of the following. Okay, so we're going to work through a few of these. Part A, cosine theta, we're looking for theta here, equals tangent 25 degrees. Well, recognizing that cotangent and tangent are cofunctions, we can use the cofunction identities that we just looked at. Okay, so we know that this is true. This was given. Cotangent theta equals tangent 25 degrees. But we know, because cotangent and tangent are cofunctions, that this cotangent theta is exactly the same as tangent 90 minus theta. So the complementary angle here. Okay, and that's going to allow us to break this down. Tangent of 25 degrees is tangent of this, 90 minus theta. And so if you think about it, if tangent of an angle equals tangent of an angle, then the angles are equal, or arguments if you want to call them that. The arguments are equal. So 90 minus theta must equal 25 if the tangent values are going to be set equal. And so if you just subtract 25 and add theta, we get theta equals 65 degrees. And you can always check on your calculator. You can type in, since there's probably not a cotangent button, you can type in 1 over tangent 65 and then separately tangent 25, and you'll get the same answers. Okay, let's try part B. So sine theta equals cosine negative 30 degrees. And recall that sine and cosine are cofunctions of each other. Okay, so we're going to rewrite sine in terms of cosine. So sine of theta is the same as cosine theta, cosine 90 minus theta. Okay, so we're just rewriting the left side. And now, if cosine of this argument equals cosine of negative 30, then 90 minus theta is negative 30. And then adding theta to the other side, adding 30, we get theta equals 120. Okay, let's try this example here, part C. Find one value of theta or x that satisfies the following. Cosecant 3 pi over 4 equals secant x. Okay, so we're looking for x in this case. We're going to go ahead and rewrite secant in terms of cosecant because cosecant and secant are also cofunctions. Okay, so secant x is the same as cosecant 90 or pi over 2 minus x. Okay, so complementary angle here, secant and cosecant are cofunctions. Now, just like on the previous two examples, cosecant of this angle equals cosecant of this argument, so those must be equal to each other. So 3 pi over 4 equals this argument, pi over 2 minus x, and then if you add x to the other side, subtract 3 pi over 4, common denominator, we end up with x equals negative pi over 4. Final answer. Okay, so quick note, because our trig functions or circular functions are periodic, meaning they do repeat after one period, every example or solution in this example, parts A, B, and C, they weren't unique. We only got one out of infinitely many answers. And so notice we were even told, just find one. Okay, and it's because these values repeat if you think about traveling around your unit circle. Okay, let's try this example. This is saying to write cosine 180 minus theta as a trig function of theta alone. Okay, so think about what this is saying before we move forward. Cosine of 180 degrees minus theta. So what we're trying to get to is something without another angle in it, just theta. So in our answer, we should only see like cosine of theta or sine of theta. We shouldn't see other angles. Okay, so recognize, hopefully, that this is cosine of a difference of two angles, and you can use your difference identity for cosine to break this apart. So if you think of 180 as A and theta as B, cosine A times cosine B plus sine A times sine B. Okay. And now we know two of these values. We know cosine 180 and we also know sine of 180, either from your unit circle or your calculator. And so cosine 180 is negative 1, sine 180 is 0. So our final answer here is negative cosine theta. So cosine 180 degrees minus theta is rewritten with just cosine of theta. So it's actually negative cosine theta. And that's exactly what the question was asking. Rewrite this as a function of theta alone. Notice there's no other angle values here. All right, let's try example 4 here. Suppose that sine S is our arc length or angle, is 3 over 5, and cosine T, so T is another angle, negative 12 over 13. And both S and T are in quadrant 2. Find the sum, so the cosine of the sum of those two angles, of cosine of S plus T. So I want you to recognize before we move forward that we don't know what the angle S is. We do not know what the angle T is, but we just know two things about them. We know sine of this angle S, and we know cosine of this angle T. So you can do this one two different ways. I'm going to show you both. Method one is going to be to use some triangles. We're going to sketch some triangles. So sketch an angle in quadrant 2 that this is true about. This given value of sine is true. Okay, we know sine is y over r, and so y is 3 and r is 5. And in quadrant 2, this is what our triangle would look like. The hypotenuse is 5, this opposite side is 3, and then hopefully you're thinking how you can find x, Pythagorean theorem. And so using your Pythagorean theorem, you get x is either plus or minus 4, and then we know what quadrant we were in, and so the reason we were told which quadrant is so that we can pick the correct value for x. So x is negative 4 because we're in quadrant 2, and our cosine or x values are negative over there. And so now we know cosine of s is negative 4/5. Why we want the cosine value is because if you think ahead, what we were asked to find is cosine of s plus t. This is our sum formula here. So we actually need cosine s, cosine t, and sine s and sine t. And so we were given 2 out of the 4 values that we need for this formula. So we're just working on finding the other 2 values. Here's the first one that we need. We're going to do very much the same thing, but for the other value we were given, cosine t was negative 12 over 13. We know that cosine is x over r, and so if we start drawing our triangle, we get our adjacent side is negative 12. Because we're in quadrant 2, the negative is going to go with the adjacent side, and the hypotenuse is 13. And so we can use our Pythagorean theorem to find y. And so y is either plus or minus 5. And since we're in quadrant 2, sine or y is positive. And so y is 5, giving us a sine t. Sine of this angle t is opposite over hypotenuse, 5 over 13. Okay, so this was the question. We were asked to find cosine of s plus t. So we fill in the right side of the equation from our sum formula for cosine. Think of a as s and b as t. And so we're just modifying it for the letters we were given. We now know all 4 of these values. We were given 2 of them, and we found the other 2. So let's fill in those values. Negative 4/5 times negative 12 over 13, and then minus 3/5 times 5 over 13. And then we simplify a little more, and we get 33 over 65. Final answer. So recognize really fast that you never actually needed to know what the angle S was or the angle T. We just needed to know the sine and cosine values of those angles. Okay, so here's method 2. This is an option also for you. This is going to replace drawing the triangles. So you're just going to use your Pythagorean identities instead of drawing the triangles to find the 2 other trig function values that you need. We're going to get the same answer, it's just another way to get it. And if you like this method better, feel free to use this method. Okay, so we're going to use our Pythagorean identity, sine squared plus cosine squared is 1. We were told what sine of s equals, so we plug that in for sine s, and then we're going to start simplifying, square this value back here to get 9 over 25, and then subtract 9 over 25 over here. If you want to, you can work it out. You can pause it real quick and just use a common denominator to subtract this fraction. Okay. And then cosine squared is this value, so take the square root. You would technically get plus and minus 4/5, but we know which quadrant we're in. S is in quadrant 2, so we're going to have a negative cosine value because cosine's negative in quadrant 2. Okay, we're going to use the same identity, sine squared plus cosine squared of our angle equals 1, to find sine t. Okay. We were told cosine t was negative 12 over 13, so you fill that into your identity, and then you're going to square that value. And then we're trying to get to sine t, so subtract 144 over 169. Again, you can pause it if you want to work out the math. You just need a common denominator here. and then you'll square root both sides. And technically when you square root, you get plus and minus right here, 5 over 13. But again, because we're in quadrant 2, we know that sine is positive in quadrant 2, so we pick the positive value. And then we would fill in these 4 numbers into our sum formula for cosine, and we would get the same answer we got from method 1. All right, we're going to just run through a quick example for an application of using these formulas. So a common household electric current is called alternating current because the current alternates directions within the wires. The voltage V in a typical 115 volt outlet can be expressed by this function. So V is voltage, voltage of time, T represents time, equals 163 sine of omega T. So W is actually Greek omega, where omega is the angular speed in radians per second of the rotating generator at the electrical plant. And T is time measured in seconds. Okay, so a lot of information there, but we're basically just going to be working with this function. All right, so part A, it is essential for electric generators to rotate at precisely 60 cycles per second. So household appliances and computers will function properly. Determine omega for these electric generators. Okay, so we're trying to find the value of omega. All right, each cycle is 2 pi radians, and if you think about it, that's because if you're rotating, a full rotation is 2 pi radians. Okay, and 60 cycles per second, and so our angular speed is going to be 60, that's our cycles per second, and times our radian value, our angle, 2 pi. So we get omega is 120 pi radians per second. All right, I'm just going to show you a quick graph. You don't have to worry about drawing this. I just want you to see it. So we're going to graph our voltage function in this small window. Okay, now that we know omega. And so notice this represents time here. This is a really short amount of time, 0.05 of a second. And so we have our sine wave. Notice it starts at 0, 0, and the amplitude goes up to 163. And hopefully you realize that from here, seeing this 163, this height of this wave is 163. And then notice you have 1 full cycle right here. And then over this length of time that's in this window, we actually have 3 full cycles. Cycle 2 and 3. Okay, so this repeats 3 times in this short amount of time. Part C says determine a value of phi, so this is the Greek letter phi, so that the graph of our voltage function, notice this is now rewritten with cosine, is the same as the original graph we just looked at. So basically this is why this applies to this section. We are asked to rewrite sine of some value, some angle here, omega t, in terms of cosine, but specifically cosine of a difference of 2 angles. So omega t minus phi, and we were asked, well, what is this number? What is this value phi? Okay, so let's break this apart. First, we're going to use our cofunction identities. We know that cosine and sine are related if we have the complement of the angle here. So sine of x is the same as cosine if we do like 90 degrees or pi over 2 minus x. So this is the same as before when we were talking about cofunctions a few examples back. All right, so we're going to use our actual letters for this problem. So instead of x, we have omega t. And so this is equal to sine of omega t is equal to cosine pi over 2 minus omega t. All right, so we're going to start to break this down a little bit. Next step, just rearrange. Because of what we were asked up here, we were asked to find omega, to work with omega t minus phi. And so all I did here was rearrange. I put the minus omega t in front, the positive pi over 2 in back. Okay, and here's why. Now if I factor out the negative, this looks like omega t minus something. Right, this looks like this should be our phi value right here, pi over 2. And it is, but let me just remind you why this is going to be the answer. Even though we have this minus sign here, recall what we know about cosine. Cosine is an even function. So if you have cosine of negative theta, it's actually the same value as cosine positive theta. So what that lets us do is basically just forget the minus sign here. It's going to be the same value. And so this is exactly what we were asked to find. Cosine omega t minus phi. So that means pi over 2 is in fact our number we were looking for, phi. So therefore phi is pi over 2. And so our voltage function can be rewritten either with cosine or with sine. Okay. So we rewrote our sine function here in terms of cosine. All right, our last example of this section, we're going to verify an identity. So we're going to verify that this identity is true. Okay, we're going to start with the more complicated side, and in this case, it's the left side. So we're going to start breaking apart the left side, and secant, we're going to rewrite it in terms of cosine. So secant is 1 over cosine, keeping the original argument. Okay, and now notice what you have. You have cosine of something minus something. So this is like cosine A minus B. So we're going to use our difference formula and break this denominator apart. Okay, so I'm going to just use A and B so you can see it. Cosine A times cosine B plus sine A times sine B, where A was 3 pi over 2 and B is x. Okay, and we know 2 of these values. So the cosine 3 pi over 2 and sine 3 pi over 2, we know both of those from our unit circle. So let's go ahead and put those numbers in. Cosine 3 pi over 2 is 0. Sine 3 pi over 2 is negative 1. And so that simplifies to 1 over negative sine x. And remember that 1 over sine is in fact cosecant. So this is in fact negative cosecant x. And we verified. All right, so that's the end of this section.